Hello and welcome to the second part of Lesson 12.4. In part 1 we looked at counting outcomes, and now we're going to use some of that stuff from the part 1 video, but we're going to focus more so on the theoretical probability. So the objectives for our part 2 video is to find theoretical probability by counting outcomes. Theoretical probability is actually the same or very similar to the probability that we've been calculating all along. Notice, to calculate the probability of an event happening, we're going to take the number of favorable outcomes and divide it by the total number of possible outcomes. Now, sometimes to find the possible outcomes, we are going to have to use the counting principle or the tree diagram if you prefer. Another word I just kind of wanted to throw out there is a sample space. Because you'll see this kind of come up every now and then. And sample space is nothing more than a list of all the possible outcomes, which would be the denominator of your probability. So with this, let's go ahead and look at a few examples. Now, example 4 says to use a tree diagram to find the sample space for tossing 2 coins. So the sample space means the number of possible outcomes for tossing 2 coins. Then we're going to find the probability of tossing 2 tails. Okay, so the first part says that we are going to find the sample space or the number of possible outcomes for when we toss 2 coins. Okay, you could use counting principles if you wanted to, but for this example, we'll use a tree diagram like it indicated. So our first option, when you go to toss a coin, let's say we get a heads. Okay, if we get a heads and we flip that coin again, we now can get a heads or a tails. Let's say instead of tossing a head though the first time, we would have tossed a tails. When I go to throw that coin again, we can get a heads or a tails. So when you add these up, okay, to find our sample space, we can see that we have 4 different we have 4 outcomes total. So this gives us 4 outcomes. So when we go to find our probability, so our probability has to have a 4 in the denominator. Now we have to find the number of favorable outcomes. In other words, when I look at these 4 possible outcomes, I want to know the probability of tossing 2 tails. So I can get a heads, I can get a heads, tails, we can get a tail, heads, and we can get a tail, tail. Well, we want 2 tails, so the only option for 2 tails out of those 4 tosses is going to be 1 favorable outcome. So the probability of throwing 2 tails when you flip 2 coins is going to be 1 out of 4 possible outcomes. Example 5 is similar to example 4. Here we're going to use a tree diagram to show the sample space for guessing right or wrong on true-false questions. So to do the tree diagram portion, okay, if you guess true on the first question and we get it right, I'm going to write R for right. And then I have 2 possible outcomes for my second question. Okay, I'm either going to get that one right or I'm going to get that one wrong, which I'll put a W for wrong. When I go, let's say my first choice, let's say I wasn't right on the first choice, maybe I was wrong on the first choice, but when I go to answer my second question, I have 2 possibilities. I can either guess that one correctly or I can guess it incorrectly. Either way, you can see right here that we have 4 possible outcomes. Okay, or this is our sample space. Now, the second part says, find the probability of guessing correctly on both questions. So again, if you look at this, in my green box up at the top, I could get my first question is right, the second question is right. I could have guessed the first one right, the second one wrong. Down below here, I can see that my first question could have been wrong, my second one was right, or my first and my second one could have been incorrect. So at that point in time, to answer both questions correctly, there was only one out of these 4 possible outcomes. So the probability then is going to be one possibility, which is where I had both of them right, out of 4 possible outcomes. So our probability here would then be 1/4. Our final example is a little bit more complex. So in this case, I probably wouldn't use a tree diagram. I would actually just use my counting principle. It says in some state lotteries, the winning number is made up of 4 digits chosen at random. So we have 4 digits chosen at random. Suppose a player buys 2 tickets with different numbers. What is the probability that a player has a winning number? So the first thing I always like to do is I always like to find out what are my possible outcomes, or what is my sample space. So to do that, we know that we have a 4-digit number. So I'm going to put the first digit, we're going to have our second digit, our third digit, and our fourth digit. Okay, so I'm going to look for my possible outcomes. When I go to find my outcomes, it says that I have, the digits are going to be chosen at random. So if you look at your numbers, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 through 9 gives you 10 different number possibilities. When you go to select the second digit, you again have those same set of 10 numbers to choose from. And remember, the 10 is coming from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. You can count these out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 number possibilities. So when I go to pick the third digit has 10 possibilities, just like the fourth digit does. So based on our counting principle, if we multiply these all out, 10 times 10 times 10 times 10 is actually going to give us 10,000 different, or 10,000 total outcomes that are possible. So now when we go to calculate the probability says that we have our probability, probability is going to be the number of favorable outcomes. Well, I bought 2 tickets. So 2 tickets is my chances to win, and I'm going to divide that by the number of possible outcomes. Well, this 10,000 right here is my possible outcomes. So I really have 2 out of 10,000 possible outcomes, which is really a 1 in 5,000 chance. So this is why playing the lottery isn't really in your favor typically. Okay, please let me know if you have any questions. Otherwise, have a good day. Thanks.